Okay, I'm ready. You can't get closer than that. Sounds okay to me. So we've got two kinds of Penrose diagrams. One corresponding to what happened if we looked at retarded time, our theta phi coordinates. And the other is what we got when we looked at VR theta phi coordinates, advanced time. And obviously both of these somehow have some relevance to what's going on. And so clearly the place where things are going wrong, or at least not going right yet, somewhere around here at the end point of the horizon that we've constructed. So, and that's this point here. So this is going to be somewhere near v equals plus infinity, and I beg your pardon, u equals plus infinity, and here v equals minus infinity. So what one really wants to do is to sort of look at this crossover point to see if you can get rid of whatever is happening here. So you might try to say, well, let's try and look at simultaneously little u, little v, theta phi coordinates, as opposed to vr theta phi or ur theta phi on its own, as maybe that will somehow make things a little bit better for us. So if we try to do u, v, theta phi coordinates, then you discover the line element is equal to ds squared equals minus 1 minus 2m over r du dv plus r squared into d omega 2 squared. What you discover is, of course, now that r equals 2m is singular. It's a coordinate singularity again. This problem was first overcome by Kruskal in 1963. And he constructed a slightly different set of coordinates based on little u and little v. By a very simple trick, he just took the exponential of them. So he defined in this region here the following objects. Big V is equal e to the little v over 4m. Big U is equal to minus e to the minus little u over 4m, and rewrote the metric in those coordinates. Now this is a very innocuous transformation. All you've done is to take the exponential of something, but if you work out what the line element is in these variables, you will get let's see, I don't want to do the calculation explicitly, so you just get ds squared is equal to 16m squared, some overall constant, and e to the minus r over 2m divided by r d big U d big V plus r squared d omega 2 squared. And that's it. There isn't anything else. If you stare at this metric, of course it's a function of u and v. R is implicitly determined from big U and big V. That's simple to see because if you looked at the product of u, v, That's equal to minus e to the v minus u over 4m, which is equal to minus e to the minus 4m, and then v minus u would be t plus r plus 2m log the modulus of r minus 2m over 2m. Minus u is minus u minus t plus another one of these plus another one of these. So this is, that should be divided by. So this is equal to minus e. T minus t gives me nothing. R plus 2m log modulus of r is 2m over 2m, and then 2m outside the front. So from the product of u and v you can calculate r, but not in terms of nice functions. But if you knew what r is, you can figure out what u and v are going to be. So what happens? This thing is obviously time reversal invariant, and so you end up with a picture that looks something like this. This surface here corresponds to big U equals 0. This surface here corresponds to big V is equal to 0. And this was the surface that was the past horizon. This is the surface that was the future horizon. And nothing peculiar happens there. These lines just simply mix. But there's nothing stopping you being either positive or negative once you have got to this stage, because you can just replace everything by moduli. This thing you don't care about. And so what you discover is that you can continue the whole thing in a way that looks like this. In this region, the way in which I have done it here, I have got u negative, v positive. In this region I've got u positive, v positive. Here I have got u negative, v negative. Here I have u positive and v negative. What you see is that this region here is isometric to this region here. Let's give these some labels. 1, 2, 3, 4. So region 1 is the original region that one imagines as being exterior to a black hole. And of course you see it's exterior to a white hole. If you're sitting here, you can happily proceed outside the black hole or the white hole in a region which is asymptotically flat. Out here the curvature is 0. So if, however, you decided you were going to fall in through the horizon like this, then you could end up in the singularity, must end up in the singularity. If you are in this region here, you could come out in that direction, or that direction, or if you chose your directions very carefully, you could go that way, but you must have come out of the singularity. Region 2, well, region 2 corresponds to the interior of a black hole. Region 3 is, if you like, a sort of mirror image of this region. It's a new asymptotically flat region equipped with its own infinities. Region 4 is the interior of a white hole. This region here is completely disconnected from this region here. If you are in region 1, you cannot get into region 3. It's causally disconnected from this region. If you are in region 1, you will be able to construct a nice asymptotic region with space-like, time-like, and null infinities like this, and you will see that this represents a horizon because it is the causal boundary of this scri plus. Similarly, if you were in this region, this thing would be a horizon corresponding to the causal past, boundary of the causal past of this scri plus. But I want to emphasize that region 3 is something that you cannot ever communicate with. The only way in which you could ever get from here to here would be, of course, along this null line, which seems a bit implausible because we don't really believe in white holes. But this region here, the so-called crossover region, there's nothing singular about it. It corresponds to r equals 2m, where capital U and capital V are both equal to 0. So the crossover region is perfectly well defined. It's at r equals 2m. There's nothing wrong with this metric. So it's well defined geometrically. That's the entirety of the space-time. It's just simply that this is another copy of this. Regions 2 and 3 are the interior and exterior of the black hole, interior of the black hole or the white hole. And then this surface here, at first sight, seems a little bit strange. So let's explore its geometry a little bit. So I want to think about what happens when t is equal to a constant and theta is equal to pi by 2, corresponding to the equatorial plane of the two spheres. If you do that, you will see immediately that in r phi coordinates, the metric is equal to dr squared divided by 1 minus 2m over r plus r squared d phi squared. So what that tells you is that sections through this thing are circles of radius r. Fixed r gives circles of radius r. This thing looks singular, but again, it's a coordinate singularity, and the easy way to deal with it is just to make a simple transformation. So let's make a simple transformation and get rid of this coordinate singularity. So let's put r equal to 2m cos squared theta. Then dr is equal to 4m cos theta sin theta d theta, and the metric becomes ds squared is equal to let me just write it down, 4m squared cos to the fourth and then an r squared, which is 2m cos squared theta d phi squared. So you can sort of see exactly what's going on here, nothing peculiar. If r goes to infinity, this just becomes circles of proper radius r. As r goes to 2m, that's as small as you can get. If you start off by looking at constant t and you go in this direction like this, what you're doing is you're decreasing r as you come in this direction. It reaches a minimum at r equals 2m, but since this region is isometric to this region, it increases again here in this direction. So the minimum is at r equals 2m, and you'll see that this thing corresponds to theta equals 0, where nothing peculiar happens. Cos to the fourth goes to 1. This thing has got radius 2m. And so you can draw a picture of what this thing looks like fairly easily. There is a region which looks just like a plane. That's for large r. It looks like it's just going to be r2. But as you decrease r, essentially these circles here of constant r will start to shrink, but instead of shrinking to 0, as they would if it was just the plane, they shrink to a minimum length, it looks like this, and then it starts to expand again. So what you see is what looks like two planes joined together by a sort of funnel. The technical name for this is an Einstein-Rosen bridge. But everybody calls it a wormhole. For the simple reason that it just looks like a hole which joins two asymptotic regions that look like planes. But I want to emphasize that this is entirely space-like. This isn't something that you can start off here and get into this region of space-time. It's something where you could traverse if you were able to move along space-like directions, but in practice you are not. It's space-like and therefore is not something that you can probe by any method. We don't like region 4, and in real cases of gravitational collapse, there really will not be an analogue of region 4. We'll come to that a little bit later on. Region 2, the interior of the black hole, is something that you can never do without. Region 3 looks like a fiction, because if you didn't have this region, why would you have this region? And indeed, until fairly recently, it was thought to be completely and utterly irrelevant, just a piece of mathematical fiction. However, recent work of Maldacena, having to do with possible resolutions of the information paradox, reveals that maybe there is something more exotic you can do with it, and perhaps we can briefly discuss that a little later on. I don't guarantee we can get that far, though. So that's, roughly speaking, the Schwarzschild metric. There's some differences between the Penrose diagram of an asymptotically flat space-time and a black hole space-time, which one really needs to keep in mind let's go back to this picture. In Minkowski space, all null geodesics started and ended at scry. That's not true here. Here is a null geodesic. It starts at scry, but it ends at the singularity. What about time-like geodesics? Time-like geodesics in Minkowski space always started at I minus and ended at I plus. That's not true here either. Here is an example of a time-like geodesic, again, which impacts the singularity. So those things make a considerable mathematical difference to various kinds of problems in black hole space-times. In Minkowski space, null geodesics always ended at scry plus and scry minus, but here is an example of a null geodesic that doesn't even look like a null geodesic. And it's something that you can't do in Minkowski space. This could be a null geodesic. Now this is of course a bit of a cheat. You can explicitly calculate all geodesics in the Schwarzschild metric. If you do that, you will end up discovering they can be integrated exactly in terms of elliptic functions, but some of them are much easier than that, and in particular you'll discover that r equals 3m is a null geodesic where the geodesic just simply is in orbit around the black hole. Nevertheless, it is still true that there are horizons, usually called H, called H plus for the future horizon, which is the boundary of the causal past of scry plus. That's the black hole horizon. The white hole horizon is the boundary of the causal future of scry minus. Of course, you have to decide which scry that you're talking about, because there's these ones and these ones. Well, so much for the Schwarzschild metric. What you've discovered is that r equals 2m corresponds to a horizon. One really nice property of the Schwarzschild metric is that the horizon shields you from the singularity. If you do not stray into this region, the singularity will be of no consequence to you. So if you stay outside the horizon, what happens here never will affect you. That's because all points on the singularity are space-like separated from here, or in the future. Unfortunately, this is not true for the past singularity. It's really only true for the singularity in the future, so perhaps I should put in the word future at this point. This is an example of what is usually called cosmic censorship. Cosmic censorship is a conjecture. Unfortunately, it's not quite true in the way in which I'm going to state it. First proposed by Penrose in 1967, but not written up till 1971. And roughly speaking, it says that this property of the singularity is always true. If, and it's a big if, the energy conditions hold. I'll say more about those later. Roughly speaking, it says that the local energy density of matter is positive. And some version of causality is true. And lastly, the Einstein equations hold. That's a very crude statement of what the cosmic censorship conjecture is, and there are counterexamples to it in the way in which I've written, but I didn't want to get into serious technical detail about what that really means. That should shed some light on something which is an obvious problem to do with a Schwarzschild spacetime. Let's go back to just looking at the Schwarzschild metric in its original form. If you stare at this metric, nobody told you that m had to be a positive integration constant. It's just an integration constant. So you could have chosen m to be positive, which is what we did right at the beginning, or we could have chosen m to be 0, in which case we get back to flat space, which is remarkably different to the rest of the Schwarzschild metric. But there's nothing stopping us choosing an integration constant to be negative. So let's make that choice. What happens? Well, there's nothing between u and r equals 0. R equals 0 is singular. This thing does not change sign. So you can just simply get to r equals 0. So surfaces of r equals constant. Well, let's see. Is r equals constant. R always time-like. And so I can just simply draw the Penrose diagram of this thing. And it looks like this, where this is the singularity. Yes? Well, we sort of implicitly did, because when we can I come back to that point in a second? It's not going to make any overall difference to most reasoning, and in actual fact, we can absorb that possibility into something else. So we'll come back to that in a moment. Here is the singularity just at r equals 0. So this is the singularity, which could be in your past light cone quite happily. So, I mean, you could look at it, or perhaps it could look at you. And it's usually called a naked singularity because it is not behind a horizon. So it's in clear violation of a cosmic censorship conjecture, and the question is why? Well, the answer in this particular case is easy. M represents the mass of some central object, but it's negative, and that means that it would have to correspond to something with energy density that was negative, that gave rise to it in the first place, and that's not allowed. So it's generally felt that this thing can't arise as a result of some evolution. In the same way, well, in distinction to the Schwarzschild black hole arising as a result of the evolution of some sensible system. Now let's deal with the question about R negative. Let's go back to the original form of the metric. I took R to be positive, really as a matter of convention. And that's because I did that for Minkowski space. Here there is no such restriction. However, since R equals 0 is singular and represents the boundary of space-time, if there was an R negative, it's got nothing to do with what happens when R is positive. Now let's look what happens if you make R negative. Making R negative is the same thing as sending M negative, because it will keep, that sign will not change. Both of these signs would change if you change both of them. So if you change both of them, you get back to where you started from. So R positive, M negative is the same thing as R negative and M positive. So the answer is, it's sort of trivial. But, yes, it's a good question, because in more complicated situations you should always ask this question. When we come to Kerr, we will have to answer that question. So, so much for the Schwarzschild metric. A very obvious question to ask is, since the Schwarzschild metric represents a black hole space-time, are there any others? And the answer is yes. The first one that you'd come across, you might be relieved to hear there aren't very many of them. So I'm only going to talk about black holes in asymptotically flat space-times, so that they tend, so the space-time looks like Minkowski space at infinity. So there are really only two other cases to contemplate. One is what's usually called the Reissner-Nordstrom solution. This is a space-time, which is a solution not of the vacuum Einstein equations, but the Einstein equations coupled to the electromagnetic field. So that corresponds to an energy momentum tensor, which is the form FAC FBC minus 1/4 of GAB FCD FCD. I won't prove that this is a solution, I'll just tell you what the answer is. The answer is very similar to this metric. You put AT equal to Q over R, all the other components of A equal to 0. That's a particular gauge which is easy to deal with. That means that FRT, not do it that way around, FTR is equal to Q over R squared, which means there is a radial electric field corresponding to a point charge of strength Q. At least that's what we would think for the electric field at infinity. But of course an electric field contains an energy density of E squared, and so that will feed back into the Einstein equations, because its energy momentum tensor here will look like Q squared over R to the fourth. The result is a spherically symmetric static metric, which is 1 minus 2m over R plus Q squared over R squared into dt squared, plus the same thing to the minus 1 so it's static. There is a killing vector which is d by dt. The isometry group is the same as Schwarzschild, namely SO3. So this is a killing vector. It's time reversal invariant. It's spherically symmetric. And so its isometry group is SO3 times R. So on the face of it, it looks very much like the Schwarzschild metric. But in many ways, it's dramatically different. The difference comes from the fact that this function here is quadratic as opposed to linear. So this object can have no zeros, 1 0, or 2 zeros, depending on the relative values of Q and M. So one possibility is that Q is less than, the modulus of Q is less than M, in which case it's got two distinct zeros. The modulus of Q can be equal to M. That corresponds to two coincident zeros. Or lastly, Q could be greater than M. No real zeros. So let's look at case 3 first, because it's the easiest. This thing has no zeros. It's plainly singular at r equals 0. I didn't work that out, but it's kind of obvious. So case 3 corresponds to a naked singularity, just like negative mass Schwarzschild. It's worth thinking about some numbers here. What is the charge on the electron in these units? Well, the answer is it's about a 12th, roughly. It's the square root of 1 over 137.0144. So this is the charge on the electron. If Q, what is the mass that this corresponds to? So we can think of this as being the charge on something. That would correspond to a mass roughly 1 microgram. So that means that if you thought the electron was described by a metric like the Reissner-Nordstrom metric, then if its mass was less than 1 microgram, it would have to correspond to this kind of metric. That is presumably not true, and quantum effects somehow would make that all work out nicely. Or alternatively, it's simply saying that the electron is not a point particle in the same sense that general relativity could be applied to it in a classical way. So it's just in terms of getting numbers, you want to keep this number in your head, just to realize that things might be not quite what they should be for the idea that these things correspond to elementary particles. It shows you that they don't. The situation is somewhat different in string theory, but I guess there's no string theory course. Heavy states in string theory could be described by metrics like this, and in which case this thing is not necessarily violated. So what about what happens when mod q is less than m? We've got two distinct zeros. You can construct null coordinates in exactly the way that we did for Schwarzschild. It's just that you're going to have a harder time doing the integrals. I'm not going to do it explicitly because it's too horrible. But all you have to do is to recall that you just have to invent an f of r such that the f dr was equal to 1 over v. And so the simple thing to do is you get lots of logarithms and it's a bit of a mess. I'm not going to do the calculation unless someone wants me to. I can tell you the answer if you like. F. Let's suppose that the zeros of 1 minus 2m over r plus q squared over r squared are at r equals r plus or minus. Then you'll discover that f of r is equal to r plus squared over r plus minus r minus times the logarithm of the modulus of r minus r plus minus r minus squared over r plus minus r minus logarithm of the modulus of r minus r minus. That should be r equals plus and minus, and r plus is taken to be bigger than r minus. Now you see why I don't want to actually do the integrals or do anything particularly with them. So what that tells you is that the zeros of this thing are coordinate singularities and won't give you any trouble. So we can proceed exactly as we did before. We can construct Eddington-Finkelstein coordinates out of this f of r, and we can construct Kruskal coordinates by taking the exponential of the relevant coordinates exactly as before, and you'll end up with a picture which is rather more complicated than the Schwarzschild metric. So Eddington-Finkelstein chords constructed from f of r as before. That's step one. Step two is construct Kruskal coordinates by taking exponentials. The result is a very large diagram. It's infinite in vertical extent, but repetitive. I'm telling you that now because if you want to draw it, you should leave space to be able to draw it. Which is going to be an interesting trick on these boards. So let's suppose that the original region that you were looking at looked something like this. So this is a region in which we imagine that our original t, r, theta, phi coordinates are well defined. Out here there is well-defined infinity, like everywhere else in an asymptotically flat space-time. And this surface here corresponds to r equals r plus, as indeed does this surface. This one you would find using the advanced coordinates, this one you'd find using the retarded coordinates. Nothing peculiar happens when you go through those surfaces, and so you will find another region of space-time that instead of being bounded by a singularity, will be bounded by a surface where r equals r minus here. You could go through that surface and reach a region where there is a singularity, and it looks like that, and this is at r equals 0. So the very first difference is kind of blindingly obvious. There is an extra region of space-time bounded by the surfaces r equals r plus and r equals r minus, which are both null surfaces. That sort of follows really from the fact that these things are 0. So both r equals r plus and r equals r minus are null surfaces. But you could have gone the other way. You could have started here and asked what happens if you try to construct the analogue of a white hole. Again, you'd find that there were these surfaces here at r equals r minus, which are the boundaries of such a region, but you could find another region down here which contained a singularity. If I try to draw lines of constant t and constant r in this thing, then in the original picture, I can't remember what we used, green for constant r. So constant lines of constant r would look something like this in this region. but in this region they would look something like this. And in this region they go back to looking like this. So in terms of the metric variables, this is sort of like t and r have swapped over their nature as you go across these null surfaces. Similarly, lines of constant t behave like this. There's nothing wrong with the tr theta phi coordinates in this region. You can use them if you want. It's just you can't use them to go from here to here, or from here to here. If you constructed Kruskal coordinates around this point, you would find a mirror image of this region, which looks something like that. I think that's right. So that's what happens. You can do Kruskal around there. But I could have done Kruskal around here just as well. And I discover another singular region that looks something like this. Or around here. And I discover a singular region that looks something like this. But then I could have observed that this region here, all of these, are isometric to all of these, and so I could just simply keep going. In both directions. If you try doing this for a little bit, eventually it will get out of control. It's really very easy to make a mistake here. And this sort of tower goes on forever. I won't draw any more of it, but you get a structure that looks like that. So that's what happens for the Reissner-Nordstrom metric in the case that the modulus of Q is less than m. There is, however, an interesting subtlety. So you'd have to ask yourself, for a charged black hole, do you really have all these sort of asymptotic regions, an infinite number of them? Here, 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 and so forth. On this side, all of those that are distinct. I don't know the answer to that, but there is an argument which says that there is something fishy about it, which is the following. You can take perturbations of this space-time. And so, for example, I could just think of doing a scalar field calculation. And what you'll discover is that scalar fields that are finite on Scri and R plus blow up on R minus. So that makes you wonder whether this surface here at r equals r minus is actually stable. And by unstable I mean to small perturbations. So it may well be that this infinite tower of stuff is an artifact of demanding staticity everywhere, and if you considered a time-dependent space-time, this thing wouldn't happen. It really is not known whether that's true or which the actual case is. Notice that this singularity is time-like. Science fiction authors delight in playing with the Reissner-Nordstrom space-time because here's an example of a region of space-time which you can travel through and get to another nice region of space-time. So for example, this bit looks like the exterior of a charged black hole. I could in principle move along the following time-like path and end up in another region of space-time that looks like an asymptotically flat region outside a black hole. Well, that's fine. The trouble is, of course, that here you'd have come out of some kind of white hole horizon, but not necessarily out of a singularity, because the singularities are time-like. That does not allow you to have time travel. It just simply says that there are regions which are disconnected and allow you to do that. But of course, perhaps we're all really mathematicians at heart, and a mathematician would say, well, that's not true at all. Let's consider the following picture. Because this region is isometric to this region, I could just simply cut the whole picture and identify. So let me try to do that. It's not as easy to draw as you might think. This region is isometric to this region. So if I was a geometer and nothing else, I would simply say, well, I can cut this thing here, construct this, take this thing here, construct a surface that looks like this, construct a surface that looks like this, and identify these two. And of course that's still a solution of the Einstein equations. That's terrible, because I could start here, I could go to this point here, I could actually keep going a little bit and end up, say, there. So that would be this path travelling to the future, but ending up in my past. That's plainly ridiculous, but there's nothing mathematically wrong with it. If such things happen, this is generally referred to as causality violation. And the consequences of that are easy to understand and horrifying to contemplate. So I won't contemplate them. But nevertheless, there's mathematically nothing wrong with doing that. So that's something that you can do with the Reissner-Nordstrom metric. And of course, this means that you could do time travel, but there has to be something wrong with that picture. If you want to forbid it, you have to invent a new law of physics which says you can't do it. Those who study ADS might want to contemplate that within the context of ADS. Yes? Well, it's not nothing to do with worrying about cosmic censorship. It's just simply that as a solution of the field equations, it's terrible. because it gives rise to causality violation. But if you want to eliminate causality violation, you've got to simply say, I'm going to eliminate causality violation because I don't like it. It doesn't violate anything else. You can do the same in flat space. You can just simply take surface t equals constant and identify it to make a cylinder in time. Nothing wrong with that. It's still a solution of the Einstein equations. It's just not one that you like. It may be even one that you don't like. It's almost the same thing. So, assuming that things like that don't happen, we should proceed. There is the third case, which is when mod q equals mod m. Sorry, mod q equals m. In a way, this is a vastly more interesting example. So this was case 2. Mod q is equal to m. So what has happened is that this surface r equals r plus and r equals r minus has been sort of forced to merge with each other. What happens? Well, first of all, we can calculate f of r and find Eddington-Finkelstein coordinates. I'm not going to do the integral, but I will tell you the answer. F of r is equal to r plus 2m log modulus of r minus m plus m squared over r minus m minus m squared over r minus m. So you can construct Eddington-Finkelstein coordinates just as before. And if you started off in some region over here, again, this is another example of a metric that is going to go on forever, so make sure you leave enough space. Here is the asymptotic regions. But now you have this surface where r is equal to m, which is null. And that corresponds to here. If you go through that, you'll find yourself at the singularity. You could have done that in the past, and you'll end up with a picture that looks like that. But this region is isometric to this region, so it just goes on forever. We get a picture that looks something like that. In a way, it's sort of easier than it was before. There is, however, an issue which we can sort of start to look at here. There's some dramatic differences. Suppose that I took lines of constant r again. They were lines that looked something like this in this picture. But as you cross the horizon, now they don't change their character. That's because it's a coincident zero, it's a double zero, and so that object that was in brackets just goes through zero and then goes back up again. So lines of constant r in this region look like that. Similarly, lines of constant t always look like this. that has a dramatic effect on something. Unlike the case of the Schwarzschild metric, or Reissner-Nordstrom with q less than m, it's still the case that there is a killing vector psi a, which is equal to 1, 0, 0, 0, with its indices upstairs. But this is now time-like everywhere, except on the horizon. Where it is null. That's in distinction to what happened for q less than m and for Schwarzschild, where in the interior psi a became space-like. The meaning of that may be useful to us on Wednesday. There's something else which is special about this thing, which doesn't really happen in the other spacetimes, and that is that this spacetime has got an internal infinity. You might ask, what happens if I try to go in this direction, in a space-like direction along a surface t equals constant? I don't get outside these two lines, because these were null lines. I go somewhere in the middle. What do I actually find? Well, we've sort of done this calculation before. What you find is an infinitely long throat. Perhaps the way to do this is to look at the metric again. And I'm going to write the metric in a slightly different form. Because q is equal to m, we can write ds squared as equal to minus r minus m all squared over r squared dt squared, plus r squared over r minus m all squared, dr squared, plus r squared into d theta squared plus sine squared theta d phi squared. So I want to put t equal to a constant. I want to put theta equal to pi by 2, the equatorial plane again. And look at the geometry of the r theta, so the r phi plane. That's basically easy. We just look at the induced metric that you get. So again, for fixed r, these are circles of radius r. Since the metric was originally spherically symmetric, I could of course promote those to two spheres. So let's define a new coordinate lambda such that d lambda is equal to r over r minus m dr. We can all do this integral. Lambda is equal to r plus m log r minus m. And in terms of these coordinates, this is going to look like ds squared is equal to lambda squared, sorry, d lambda squared plus r squared d phi squared, where r is determined from lambda here. So what happens? You can make r as small as you like, but you'll see that as r goes to m, lambda is going to minus infinity. So that tells you that r equals m, the proper distance down to r equals m, if you just start decreasing lambda, is going to be infinite. So what that tells you is that there's a sort of internal infinity. You found it by asking for what happens when you take the Einstein-Rosen bridge and just simply stretch it. It's the easiest way to think about it. If you do that, you'll lose one half of the bridge, because this sort of wormhole goes on forever. So this is really an internal infinity. So if you went off, which you obviously can't do, but if you went off in a space-like fashion here towards r equals m, you would keep going forever and never reach the singularity. There's no singularity in that region. So if you go space-like towards r equals m, you don't come across a horizon of singularities, you just end up in this infinite region. If you ask yourself what is the metric at the end of that cylinder, that is to say, as r goes to m, you take its asymptotic limit, you'll discover it's ADS2 cross S2. So those interested in the ADS-CFT correspondence have made some mileage out of that fact. So that was a single black hole. For these black holes, it turns out that you can discover something rather strange on the face of it, and that is that you can superpose them. This is originally due to Majumdar and Papapetru. They found a metric that had any number of these Reissner-Nordstrom black holes with Q equals m anywhere you like. What they did was to solve the following equations. They did this in Cartesian coordinates, which makes life much easier. So they looked at, well, let's do this calculation in a bit more detail. So it's minus u squared dt squared plus dr squared over u squared plus r squared into d theta squared plus sine squared theta d phi squared. That was the form of the metric we had it in, but you can convert that to Cartesian coordinates fairly easily. So it's equal to, now, minus 1 over phi squared dt squared plus phi squared into dx squared plus dy squared plus dz squared. So that's a nice coordinate transformation. And to make equivalence, you need to put x squared plus y squared plus z squared is equal to rho squared. And you can make the coordinate transformation work by putting phi d rho is equal to dr over u, and phi times rho equals r. And I suggest you actually try that for a single Reissner-Nordstrom black hole. What you will discover is that phi is given by 1 plus m over rho. That's it. If you calculate A0, the vector potential is equal to m over rho. The same thing. So you could just simply say, well, this is a black hole sitting at the origin of the XYZ plane. All well and good. You can calculate the Einstein equations if you assume that metric is of this form here, and you will discover the Einstein equations are del squared phi equals 0. So that immediately tells you that you can find a nice generalization of this. Where you just simply put the black holes anywhere you like. Phi is equal to 1 plus m sum over I 1 over x minus xi, and these things are vectors. You can have any number of these things you like. Actually, you can do that slightly differently. You can give them any masses you like. So that's a solution of the Einstein equations, or the Einstein-Maxwell equations. So here is space. You just simply put them down anywhere you like. Point x1, x2, x3, x4, x5, etc. Anywhere. The reason that this works is because, of course, there will be forces between these things. There will be an attractive gravitational force, between the two, which will be basically like the inverse square law. It would look like mass squared over distance squared. But equally well, there'll be an electrostatic repulsion between the two. Notice the way I've done it here is they've all got the same sign of the charge. So between each pair, there will be a balancing electrostatic repulsion. So these things are in neutral equilibrium. Now, of course, this should make you very suspicious about something. If you can linearly superpose things in a gravitational theory, then you should immediately think of things which have some kind of supersymmetry. So these are examples of BPS states that have unbroken supersymmetry. So what kind of supersymmetry could it possibly be? Well, let's just think of some simple supergravity theories. Yes? I don't know. These points, although they look like points in R3, are actually whole two spheres worth of event horizons. So the event horizon looks like a point, but that's because the coordinates are kind of bad there. So you're asking about an observer that sits here? They can't. They still look like points in these coordinates. So what you'll discover is that if you do the coordinate transformation from the original Reissner-Nordstrom coordinates we used to these sort of isotropic coordinates, you will discover that r equals m gets mapped to the point x equals xi. So all of the horizon gets mapped to one point. That's because the map there is singular. So no, the event horizons never intersect, and so this guy can look this way, see one, look that way, see the other. Quite happily sit there. As long as he doesn't gravitate, it's fine. The true singularity, gone. We don't see it here. That's because, well, we have phi is equal to 1 plus the sum of mi over mod x minus xi, and that was something that we derived. Well, actually we did it for a single thing. So we just did this, and this coordinate transformation worked for r greater than 0, and that corresponded to r bigger than m. So in these coordinates you simply don't see it. You've collapsed the horizon down to a point. Of course, it isn't really a point, it's really a sphere. So I could draw a different picture in these type of coordinates, and what I'd have is a collection of blobs. But of course, you'd never be able to spot it if you did this. I mean, the whole point of changing coordinates is this, so that you can see that solutions of Laplace's equation do the right thing. So you just have a collection of things there. If you want to go to the singularity, be my guest, fall in any one of these things. They will all have different singularities. I can't draw that. All the interiors will look like the interiors of the original one, but they're all different. It's the magic of coordinate transformations. It always causes a great deal of trouble. So, what kind of supersymmetry? Well, in supergravity, let's just do n equals 1 supergravity. Apologies if you have not done any supergravity. The symptom of finding something which is supersymmetric is to say that the change in the gravitino field is 0. So that means that there is a spinorial field, epsilon, that when you take its covariant derivative will give you the variation of the gravitino, and this is equal to 0. Solutions of this equation are usually called the killing spinor equations. Which in a way is analogous to the killing vector equations. If you think about this for a moment, there are 4 complex objects in here, and there are 4 directions, so there are 16 equations for 4 unknowns. And so you'll be lucky to be able to solve them. For n equals 1 supergravity, there are only in dimension 4, there aren't many solutions. 2 to be precise. Flat space. And plane wave spacetimes. Roughly speaking, this thing has as many supersymmetries as possible. This has got half of them. But of course, here we're talking about a theory which contains a vector field, and n equals 1 supergravity does not contain a vector field. And so this thing you want to change to n equals 2, which contains 1 graviton, 2 gravitini, 1 vector field. And the analog of this equation becomes a little more complicated. It is, roughly speaking, covariant derivative of epsilon plus, beg your pardon, minus with my conventions, 1/4 of FA FBC, gamma B, gamma C, gamma A, epsilon equals 0. Again, this is epsilon is complex. This equation is 16 equations for 4 unknowns, and generally you can't solve these equations. But in this particular case you can. I'm not talking about gauge supergravity. There are, in fact, precisely 3 possible solutions to this. 1, flat space. 2, plane waves. And 3, these Reissner-Nordstrom solutions with Q equals M. So the point of this diversion is to tell you why it is that these things play some role in any supergravity theory, or indeed any theory that has supergravity as a low energy limit as some special states. So that of course includes string theory. So somehow there is something special about these objects. I think it's not ultimately understood what exactly is special about them, but that you should certainly know that there is something very different about them. And when we come to look at the Hawking effect, we will see some other important differences between this and ordinary black holes. So, it's now 4:30. There's been a slight change of schedule so that some people can get a train at whenever it is. So we will swap 2 lectures on Tuesday. I will do the afternoon, but I'll take an extra half hour to do it, thereby making up for the half an hour that we're missing now. So let's stop there.